Welcome to the deep dive. Today we're looking at probably the most extreme objects in the universe. Black holes. Where gravity just crushes everything and even light can't get out.
Yeah, they're fascinating. For like a century, they were just these weird predictions from physics equations.
Yep.
But now we actually see them shaping the cosmos.
So our mission today is to give you a shortcut, really. A path from the theory, from Einstein's ideas, right up to the amazing direct pictures we've seen recently.
And the place to start isn't Newton's gravity, not really. We need to jump ahead to 1915. Einstein. General relativity. That's the bedrock for understanding black holes.
Right. Einstein didn't see gravity as a force, did he? It was more about geometry.
Exactly. He saw space and time as interwoven. A single four-dimensional thing called space-time.
And mass bends it. That's the famous analogy, isn't it? The bowling ball on the stretched rubber sheet.
That's the one.
Yeah.
The bowling ball is the mass, say the sun. It creates a dip.
And planets, like marbles, just roll around in that dip following the curve.
Precisely. Now, imagine that dip becoming infinitely deep. That's essentially a black hole. Colossal mass squeezed into zero volume, creating a gravity well so intense.
That the speed you'd need to escape is faster than the speed of light.
And since nothing can go faster than light, nothing escapes.
Okay, let's talk about that edge, the boundary, the event horizon.
Right, the event horizon. It's crucial. It's not a physical surface you'd bump into, more like an invisible sphere. The point of no return.
And its size depends on the mass inside.
Yep, that's the Schwarzschild radius, named after Carl Schwarzschild, who figured it out pretty quickly after Einstein published his theory.
So what makes it the point of no return? Is it just the immense gravity, or...?
It boils down to escape velocity. At that exact boundary, the speed you need to pull away equals the speed of light.
Ah, okay. And since nothing can hit light speed...
Anything that crosses it, even light itself, is trapped. Forever.
This is where things get really weird with time, right? Relativistic effects. If I'm watching someone fall in...
From your perspective, safely outside, time for the falling person would appear to slow down dramatically.
Like watching a movie in slow motion.
Even more extreme. Their image would get dimmer, redder, that's redshift, and they'd seem to freeze right at the edge.
Freeze, like forever.
From your view, yes. They'd appear stuck at the event horizon, fading over an infinite amount of time. You'd never actually see them cross.
Wow, that sounds unsettling. But for the person falling in?
For them, it's different. Time feels perfectly normal. They'd sail right across the event horizon in a finite amount of time, probably wouldn't even notice the exact moment.
Until it's too late. One-way trip after that.
A one-way trip to the center, the singularity.
Which brings up the question, how do these things even form? Where do they come from?
The most common way, we think, is from the death of really massive stars.
Okay, so we're talking stars much bigger than our sun.
Oh yeah, at least 8, maybe 10 times the sun's mass. Throughout its life, the star is in this constant battle. Fusion pushing outwards, gravity pulling inward.
A delicate balance.
Until it starts making iron in its core. That's the crisis point.
The iron core crisis. Because fusing iron takes energy, it doesn't release it.
Exactly. The star's energy source just switches off instantly.
In gravity.
Gravity wins. Catastrophically.
Yeah.
The core collapses in less than a second.
Triggering a massive explosion.
A Type 2 supernova, yeah. A huge shock wave blows the star's outer layers into space. But what happens to the core, the leftover bit, is key.
Right, there's a limit, isn't there? A mass limit.
A Tolman-Oppenheimer-Volkoff limit. It's roughly 2 to 3 times the mass of our sun.
So if the collapsed core is below that limit...
It stabilizes. It becomes an incredibly dense object called a neutron star.
But if it's above that limit...
Then there's nothing, no known force in the universe that can stop the collapse. It just keeps crushing down.
All the way to a singularity. Forming a black hole.
A stellar mass black hole. That's the first type.
Okay, so stellar mass is one category. What are the others? How do we classify them?
It's mostly about mass. Stellar mass black holes, the ones from stars, are typically, say, 3 to maybe a few dozen times the sun's mass.
And there are lots of them.
We think there could be tens of millions just in our Milky Way galaxy alone.
Wow. Okay, then what? Bigger ones?
Much bigger. The supermassive black holes, or SMBHs, these are the real monsters. Millions, even billions of times the mass of the sun.
And these are the ones at the centers of galaxies?
Almost certainly, yes. At the heart of most big galaxies, including ours. Our Milky Way has Sagittarius A, often called SGRA.
And how massive is ours?
SGRA weighs in at about 4 million solar masses. We're still figuring out exactly how they get so big. Probably started small and grew over cosmic time by merging and gobbling up gas and stars.
Any other types? I feel like I've heard of another category.
Yeah, there's the kind of missing link category. Intermediate mass black holes, maybe hundreds to thousands of solar masses.
Harder to find?
Very. We suspect they might be hiding in the centers of dense star clusters, globular clusters. Still a lot of active research there.
And one more, right? A really weird type.
Ah, the hypothetical ones.
Ah.
Primordial black holes. These wouldn't have come from stars at all.
So where would they come from?
The idea is that they formed right after the Big Bang from just incredibly dense patches in the very early universe.
Wow, do we know if they exist?
We don't. It's still theoretical. But what's really intriguing is that some people think they could actually be a component of dark matter. Tiny, ancient black holes wandering the cosmos.
Okay, that's a wild thought. Let's go back inside, conceptually at least. The singularity, what is it?
Well, according to general relativity, for a simple, non-spinning black hole, it's a point of zero volume and infinite density.
Infinite density, that sounds impossible. Like the math breaks.
It basically does. Design of general relativity isn't the complete picture at that scale. We need a theory of quantum gravity, which we don't have yet.
And what if the black hole is spinning, which most probably are?
Good point. For a spinning one, a Kerr black hole, the singularity isn't a point. It's thought to be stretched into a ring, a one-dimensional loop, a ringularity.
Does that solve the infinite density problem?
Not entirely, but it changes the geometry in weird ways. Still, it's deep into theoretical territory where our current physics gets shaky.
And spinning black holes have that other weird region, too, outside the event horizon?
Right, the ergosphere. Because the black hole's spinning so fast, it literally drags space-time around with it.
Frame dragging.
Exactly. Inside the ergosphere, you cannot stand still relative to distant stars. You are forced to rotate with the black hole.
And I remember reading something about extracting energy from there.
Theoretically, yes, the Penrose process. You could, in principle, throw something in at the right angle and have it come out with more energy than it went in with, stealing some of the black hole's rotational energy.
That's amazing. So if all this stuff falls in stars, gas, maybe unlucky astronauts and gets crushed, does the black hole somehow remember what it ate?
Ah, this leads to something really profound. The no-hair theorem. Yeah, it's a funny name. It basically says that once a black hole settles down, it's incredibly simple. It can only be described by three things you can measure from the outside.
Okay, what are they?
Its total mass, its total angular momentum, that's its spin, and its total electric charge.
That's it, just three numbers.
That's it. All the other details about what fell in, whether it was hydrogen gas or elephants or diamonds, all that information is lost, smoothed away. The black hole has no hair, no complex features.
So it has no memory of its past meals, just the total calories, spin, and charge.
Pretty much. Which is deeply weird when you think about information.
Yeah.
But, okay, even though the hole itself is black.
The area around it can be incredibly bright.
Exactly, because of the accretion disk.
Right, all the gas and dust spiraling inwards.
It gets incredibly hot due to friction and compression as it swirls around, like water going down a drain, but way more extreme. This disk can glow incredibly brightly, especially in X-rays.
And that's how we often see them indirectly.
Yes, especially the supermassive ones. Their accretion disks are enormous and powerful. And there's more.
Jets.
Colossal jets. Magnetic fields in the disk can grab some of that superheated plasma before it falls in and shoot it out from the poles.
At near light speed.
Pretty much.
Yeah.
These jets can stretch for thousands, even millions of light years. When we see these pointing towards us, we call them quasars or blazars. They are unbelievably luminous.
Some of the brightest things in the entire universe powered by a black hole.
Absolutely. They can outshine their entire host galaxy.
So finding them wasn't always about seeing the black hole itself, but seeing its gravitational effects or the light show around it.
For a long time, that was the only way. Cosmic detective work.
Like watching stars orbit. Nothing.
Precisely. That's how AGRA was confirmed at the center of our galaxy. Astronomers like Andrea Ghez and Reinhard Genzel spent decades tracking stars, whipping around an unseen object.
And they won the Nobel Prize for that, right?
Yeah, they did. In 2020, they measured stars, like one called S2, moving at thousands of kilometers per second. The only explanation was a supermassive black hole, about 4 million solar masses, sitting right there.
Incredible work. What other indirect methods are there?
Well, there are X-ray binaries. That's often a normal star orbiting a black hole. The black hole pulls gas off the star.
Forming a smaller accretion disk that emits X-rays. like Cygnus X1, the first really strong candidate.
Exactly. And then there's gravitational lensing. The black hole's gravity bends the light from objects behind it.
So you might see distorted or multiple images of a distant galaxy.
It acts like a lens, magnifying or warping the background view. But then things changed dramatically in the last decade or so. We got direct proof.
Okay, this is the really exciting recent stuff. First up, gravitational waves.
Yes. 2015, LIGO detected ripples in space-time itself.
From two black holes crashing into each other.
Two stellar mass black holes merging, billions of light years away. That event, GW150915, was monumental. It confirmed Einstein's prediction of gravitational waves and literally opened a new way to sense the universe. We could suddenly hear these cosmic collisions.
Hearing the universe, that's poetic. And then came the picture.
The picture. 2019, the Event Horizon Telescope collaboration.
Which wasn't one telescope, but loads of them linked together.
Exactly, a virtual telescope the size of the Earth. They managed to take an image of M87, the supermassive black hole in the galaxy Messier 87.
And just to be clear, it's not a picture of the black hole itself because that's impossible, right? It's the silhouette.
That's the crucial point. You see the dark central region that's the shadow cast by the event horizon surrounded by the bright glowing ring of the accretion disk.
It looked exactly like the theories predicted.
It was stunning confirmation, a direct visual of the abyss, testing general relativity in its most extreme playground. And then in 2022, they released the image of our own SGRA.
Amazing progress. But black holes still hold some really deep mysteries, don't they? Places where our physics just doesn't add up.
Oh, absolutely. The biggest one is probably the information paradox.
Okay, what's that? It involves Stephen Hawking.
Yes. Hawking discovered something amazing.
Yeah.
Black holes aren't perfectly black. They should slowly leak radiation, now called Hawking radiation.
So they evaporate over incredibly long time scales.
Trillions upon trillions of years, but yes, theoretically they shrink and eventually disappear.
Okay. So where is the paradox?
The paradox comes when you mix that with quantum mechanics. A fundamental rule in quantum physics is that information can't be destroyed. It can be scrambled, hidden, but never truly erased from the universe.
Right. But if a black hole eats, say, a book with all its information,
And then evaporates into completely random, featureless thermal radiation.
where did the information in the book go?
Exactly. Did it get destroyed? If so, quantum mechanics is wrong. Did it somehow leak out in the Hawking radiation? If so, how? General relativity doesn't allow information out. It's a fundamental clash between our two best theories of reality.
Wow. So studying black holes forces us to confront this basic conflict.
It really does. It tells us we need a deeper theory, a theory of quantum gravity,
Yeah.
to reconcile them.
And this ties back to the singularity too, right? That point of infinite density.
That prediction of infinity is probably just general relativity shouting, I don't know, at that tiny scale. It's likely incomplete.
So future theories might replace it with something else, something less infinite.
Possibly. Ideas from things like string theory or loop quantum gravity suggest the singularity might not be a point, but maybe some kind of quantum fuzzball or a tiny ultra-dense Planck star obeying quantum rules. We just don't know yet.
So much still to figure out. What's next in terms of research? What are people working on now?
It's a really exciting time. The Event Horizon Telescope team wants to make actual movies of the material swirling around said GRA to see dynamics in real time.
Movies of a black hole shadow. Incredible.
And then there's LISA, a future space-based gravitational wave detector. It'll be sensitive to mergers of supermassive black holes, potentially across the entire universe.
Hearing the biggest collisions in the cosmos.
Yeah. And the James Webb Space Telescope is peering back into the cosmic dawn, looking for the light from the very first stars and galaxies, maybe even spotting those first seed black holes forming.
So black holes aren't just cosmic oddities, they're key players.
Absolutely essential. They anchor galaxies, they power quasars, they drive cosmic evolution. And maybe most importantly, they are the ultimate laboratories for testing the limits of our understanding of physics.
It seems like the deeper we look, the more they force us to question everything. They really are the place where gravity, space-time, and the quantum world collide.
And maybe the biggest mystery isn't just what happens inside the event horizon. Maybe it's whether we humans can ever figure out a single set of laws that governs both the incredibly large and the incredibly small. That's the quest black holes seem to demand from us.